Hi everyone, my name is Hongbo, and today I'll be talking about some of the recent applications of deep learning in scoliosis assessment. So what is scoliosis and why do we care about it? Well, as you can see on the image on the right, we have a normal spine. It's very straight. However, in some people develop scoliosis, which is an abnormal deformation of the spine, as you can see on the right. And specifically for adolescent idiopathic scoliosis occurs in a youth between the age of 10 and 18 when they are growing. And this happens in about up to 5% of the general population. So progression of this disease can lead to injury to organs such as the heart and the lungs, and leading to poor quality of life. So the way to screen for this disease right now is something called the Addams test. So you would go to your family doctor and to perform the Addams test, which is essentially the patient is asked to bend over at 90 degrees, and the doctor will be looking at the curve of the spine and in order to see if there's something of concern. And when the doctor sees some deformation, you will be asked to take a biplanar X-ray image. So in AP, so front to back view, and lateral, which is left to right view. And after acquiring the image, the radiologist will be measuring, looking at those images and measuring the curve angles in order to assess the degree of scoliosis and to make clinical decisions. So for measuring this curve angle, essentially it involves looking at the whole spine, examining all the vertebrae, looking at two of the most tilted vertebrae, and then measuring the angles between those two. So typically 3 angles are considered. The main angle is between the two most tilted vertebrae, and then there's the top angle, which involves the first vertebra and the first tilted vertebra, and the bottom angle, which involves the second tilted vertebra and the last vertebra. So of course this task is very challenging because the X-ray images are usually not standardized, meaning that there's a lot of variability in both the image intensity and the quality of the images. And as you can imagine, trying to find the most tilted vertebra is slow and tedious and very susceptible to human errors. So currently in literature, there are some attempts made in trying to aid the measurement of curve angles. And so the current method is basically some segmentation or detection-based method, which involves some kind of image feature extraction using filtering. But this isn't very optimal. And there's also you also need multiple steps, so there is no way to incorporate the relationship between detecting the actual vertebra to the clinical measurement of curve angles. So there's finding also a certain amount of human bias involved because current method for segmentation requires it's usually a semi-automated, meaning that it requires some user interaction to select a region of interest. So in our lab, we have worked a bit on direct estimation methods. And the motivation of doing this is such that you are essentially trying to learn the relationship between image features and clinical features directly, as well as enabling you to use multitask learning to exploit the task dependency between locating as well as measuring. And finally, it allows a whole framework for end-to-end learning to avoid any intermediate errors in intermediate steps, such as, for example, in segmentation, you would have over-segmentation or under-segmentation problems. So with direct estimation, you avoid all those. Now, today I will be proposing, talking about two of my works on using deep learning to solve this problem. So the first paper on the left essentially does a direct estimation of the spinal landmarks for the spine. And the second paper essentially is a more sophisticated, more involving method involving both measuring the curve angle as well as the landmarks in multiple fields. So for the first paper, for the direct estimation of spinal landmarks, we use a data set of 481 AP, so front to back images, divided it into a training validation set as well as holding out 50 images for testing. And these images are taken from adolescents and taken at an image resolution of 0.26 millimeter per pixel. And as you can see, as we've talked about today, in medical image, so in deep learning, 500 images isn't very much, but for medical purposes, a lot of people would be very happy with this number of data. But of course, I'm greedy, so I want to have more data. So I also use data augmentation, like we discussed before. So I want to introduce some variation in intensity, and I did that by randomly adding Gaussian noise to the images during training, as well as adding some Gaussian noise to the actual landmarks in order to simulate the variability of detecting the landmarks. Now, my procedure involves two innovations for solving the particular problem. And so I developed a boost layer in order to so the idea of the boost layer is to create an enhanced feature space to facilitate learning, as well as having more discriminative features to during your training. And essentially what I did was first use, so this is a neural network layer. So within the layer, I used an autoencoder type of architecture, meaning that first you have the feature space, your feature space X. We first encode it into a higher feature space using the encoder W, and then decode it back using the transpose of your encoder. And this gives us back into a reconstructed feature space. And then we've tried to find the reconstruction error between your decoded image and your original feature space. And in this way, you can essentially find certain amount of outliers in your data or in your features. So with the outliers, if it's greater than a certain threshold, and in this case, 2 standard deviations, if it's larger than 2 standard deviations away from the mean, we consider that an outlier, and we replace, so we move that towards the centroid of your feature space. And in this way, you try to encourage your network to learn more discriminative features while having a faster convergence. And as you can see on this graph, we compared network trains using the boost layer as well as one trains using a normal convolution layer. And as you can see, the one with the boost layer can converge to a lower error comparing to one without the boost layer. So the next step to consider is to apply some type of structural constraint. And so since the task is to detect spinal landmarks, we want to introduce some kind of prior as constraints. So in this case, instead of having your network, having each landmark be connected to all the other landmarks, we only want to constrain the landmark to be affected to the landmarks beside it. And in this way, you essentially reduce the degree of freedom from n-1 down to 3. This means that less information is required to be learned, meaning that you would require less data for the same accuracy. And putting everything together, we have this framework. So since we're dealing with images, I've used a few layers of convolutional layers to capture the particular spinal features of the X-ray images, and then use boost layers to selectively boost relevant features. And after that, applying the spinal structures output layer to have some type of constraint as prior. Now, for the current work in the literature, there are people have only looked at the front to back images, and the reason for this is that, as you can see, it's very difficult to find the vertebra in the lateral image due to the occlusion by the rib cage. Since X-ray is a 2D modality, so all the image is essentially flattened, and this is why it is very difficult to find the most tilted vertebra in the lateral image. And this is a very difficult AI problem, and one way that to solve this problem is to consider the relationship between AP images and lateral images, because they are essentially an image, a 2D representation of the same 3D object. So there has to be some kind of relationship between the two. Now, for my second work, I am essentially using that kind of relationship in a deep learning framework to solve the problem of automatic scoliosis assessment. And for this work, the data set we use is 263 AP and lateral image pairs. And again, for the image augmentation, we introduce intensity variance as well as rotation variance, and finally some shift variance to the images during training. So, like I mentioned before, we want to capture the relationship between the two fields. So I proposed this X module network, which essentially, given your two image features, your AP feature and your lateral feature, it's first adds them together to create a fields representation of the feature space, and then concatenate those to each of the respective fields, and then do a convolution on those concatenated features for each of the fields. And the result is, as you can see on the right, I have feature maps of single field features, meaning that there are no no X modules involved in the single field features, and as well as the bottom shows the feature maps learned by the X modules. And as you can see, the X module learns more discriminative features. And if you look, I'm not sure if you can see, but if you look closely at the bottom row, so the top row, I manually made some lines to show what you're supposed to look at. So in the bottom feature space, feature map, you can actually see some type of spinal structure, whereas in the single field feature maps, you can't really detect any of the structures from the feature map. So the next task is MultiTask Learning. And in this case, what you want to do is to exploit the relationship between detecting spinal landmarks as well as measuring curve angles. So how this is done is using an iterative training method, training algorithm, which essentially for each image batch, you first, for each iteration, you first partially train your spinal landmarks, and then you train your curve angle estimator, and then you go back to training your spinal landmarks. And the reason this works is that you are essentially, remember during the first talk, we were talking about moving across the error space, in which during the gradient descent, after the backpropagation method, you are essentially wiggling your parameters closer to a minimum. So by wiggling based on both of the two related paths, you can get to a much closer local, much smaller local minimum compared to if you just do it individually. And this is shown by our results, in which I compared this iterative training method against using sequential methods. So sequential is basically just training the landmarks first until it's converged, and then train your angles next until that converges. And the angles only method is basically just, we don't care about the landmarks, we just want to train for the angles. And as you can see, just training using the angles, the error is highest compared to if you train it sequentially and training iteratively. So what this shows is that there is some positive reinforcement occurring between training both landmarks and curve angles together versus just training it sequentially or training just the curve angle. And next is the proposed joint regression loss. So in this case, typically the deep learning method, people use just a single loss function to minimize the difference between your prediction and your label. which is shown on the right. And in this case, since we are working on predicting landmarks, so if you just try to minimize the difference, you could get into the case where, while the difference is minimized, the shape isn't exactly the same. You have two different shapes. So the yellow is the prediction, and the black represents the ground truth. And as you can see, the curve of the predicted landmark and the ground truth landmarks are very different. And this will certainly affect your results. And so therefore, I introduced a second term, which is called a correlation loss. And for the correlation, it's basically trying to minimize the Pearson correlation between your ground truth and your prediction. And in this case, if you just use the correlation, well, you have the same shape, but you don't necessarily have a minimal error. This is why by combining the two, you'll have both a minimum error as well as having the same shape, which is important for measuring the curve angle. So putting everything together into the second word, we have two views, the AP image view and the lateral image view. So we first apply a convolution to get any relevant features, and then apply the joint feature learning using the X modules to learn some type of latent representation of the spine. And after that, we use the MultiTask Learning to incorporate the task-related relationship between the spinal landmarks and the curve angles in order to get more accurate results. So here we have some nice images of our detection landmark, our spinal landmark detection methods. And as you can see, using our proposed deep learning method, we can have very nice curves. And if you compare that to the machine learning methods, where the curves are not that smooth. So, and the result for the curve angle estimation, the first two papers are using basic traditional machine learning methods, and the bottom one is the multi-view methods. And as you can see, our method, the deep learning method, is much better than the traditional machine learning methods. So to summarize, the current clinical workflow is essentially the Addams test, taking the image, radiologists look at those images, find the curve angle, and then make a clinical decision. But we are hoping to go into the direction where we use deep learning methods to facilitate the clinical workflow and making the jobs easier and faster. So in this way, how our deep learning method works in the clinical workflow is essentially after getting the images, we provide them with the curve angle estimation, and then use those and other features to get some type of diagnosis and prognosis. And the radiologist or doctor can just look at all the information and then make the final clinical decision based on those. And thank you.